So let's start working on task 3 now. We have here to determine the machine representation in single precision on a 32-bit word length computer for the following decimal numbers. So the first one is -8 times 2 to the power -34, and then you have 0.03125, 492.78125. So we start with the first one now, and I have written down the steps here that you saw in the lecture, the steps 1 till 8 for converting from the decimal numbers to the 32-bit word length in the computer representation format. So here we have the first task to be done, or for the first step to be done, is to determine the sign. So as we can see over here, the sign is negative. It's a -8, so the sign is negative, and when the sign is negative, we have, for the bit representation, we'll have 1. So maybe I'll just write it here down. Oh, that's visible enough. So that's the answer to that is 1, a positive 1. But anyway, it's always positive, whether it's a 0 or a 1. The sign, if it's plus, so the sign bit is 0, and that's a positive 0. And if the decimal number is negative, then the sign bit is 1, and it's a positive 1. So I wouldn't want to write here a positive, just the sign is negative, so it's 1, the sign bit is 1. Okay, so now we have to convert the integral portion to unsigned binary. So convert the integral portion, which is this one here. So converting 8 to binary, we have 8 divided by 2. So we write the quotient here and the remainder. The quotient would be 4, remainder is 0. And then we'll have here 4 divided by 2. So you have the quotient to be 2 here, and remainder is 0, and then 2 divided by 2. The quotient is 1, remainder is 0, and then you have 1 divided by 2. So the quotient is here 0, and the remainder is 1. And then we draw our arrow upwards, and we take the number, so the 8 will be represented as 1000 in binary format, right? Okay, now the next step is to convert the fractional portion to binary. In this case here, we don't have a fractional portion because we have integer, that's 8, and so there is no fractional portion, so we just leave this part here. Then we normalize the value by adjusting the exponent here now. So our value now looks like this one here. We have 1000 times 2 to the power -34, and if you're normalizing this, it will look like, so when you normalize, you have 1 in front if it's a binary number, and then the decimal, and then whatever you are having after that. So here our decimal is right here, so what we do is we move it 3 steps forward and we put it down here. So it will be 1.000 times 2 to the power -34, but because we moved this 3 times forward, so we'll have here +3, so that will be now -31. So this now will be -31. Okay, so we have adjusted the exponent and we have normalized the value. So this is our answer to step 4. Okay, now in step 5 we add bias to the exponent. So our exponent that we got just now was -31, and adding 127 to it will give us here 96 as the exponent, and then what we do is we convert the biased exponent to unsigned binary. So we have to convert 96 to binary. But then in task 1 and task 2 you already learned how to convert it, so I'll not show it over here again. So here I'll just directly write the value for 96, which is 0 1 1 0 0 0 0 0. Okay, so that's 96 here. But then here I think when you do it you will not get this 0 over here, if I'm not wrong. Okay, so now here when you come back you have determined the final bits for the Mantissa. So the Mantissa we get it by looking at the normalized value here. So whatever value we have after the decimal point here, this value is the Mantissa. So the Mantissa for us here is, you can just say zero 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 zero. So there will be 23 zeros here because we are in the 32-bit representation. So we have 0 0 0, 4 zeros, that's 23 zeros. You don't have to write it always like that. It's just, I'm just trying to do it according to the steps over here. So for the first question we are just doing that. Now when we put it all together, we have first to write the sign bit. So the sign bit we got it as 1, and then we'll write our exponent which we got here, and the value we have to fill up 8 bits here, but we have here like 1 2 3 4 5 6 7 numbers, 7 digits here. So we put a 0 in front, and then we'll write here 1 1, and then we have 5 zeros. So that's the single bit for the sign, and then you have, you have the 8 bits for the exponent, and then we have the 23 bits for the Mantissa, which is all zeros, because here after 1 we have only zeros, so I have filled all the 23 positions with only zeros. So we'll just fill in okay. So that's the Mantissa now, and that's how it is represented in the computer, the number -8 times to the power -34. So now let's go ahead and do the second question, part B, where the number was 0.03125. Okay, so now I'll not list down all the steps once again. We'll just talk and we'll just try to be quicker now. So first step is of course to determine the sign. So you can, the sign bit here would be, it's a positive number, so the sign bit is 0. Then we convert the integer part and the fractional part. So integer part here is 0, and we don't need to convert a 0 because it will be 0 at the end, right? And then the fractional part here is this part here, which is 0.3125, 0.03125. So converting that to binary will give us the value as 0.00001 in the binary format. Okay, so that's the whole number actually. And then we have to do normalization. So we normalize the value by adjusting the exponent now. So if you're adjusting the exponent here, you know, like you have to take the decimal number in such a position that the first number should be 1. So here we have only 1 here, so we'll take the decimal number like 1, 2, 3, 4, 5 steps, and then we put it here, the decimal. So that will be 1.0 times 2 to the power, we moved it 1, 2, 3, 4, 5 times, so we have -5 here since we moved it to the right, the decimal. So that's the normalized form of the number. So once we get the normalized value, now what we do is we add bias to the exponent. So we have our exponent is -5, so I'll just write the whole value down again because it's simple to write this one. -5 plus 127, so that gives us 1.0 times 2 to the power 122. So what we're supposed to do now is take this exponent and make it to binary number, right? So we take 122, and in binary representation this number will be 111 1010. Alright, so that's the binary representation of this number here. And once we're done with that, we have to determine the mantissa now. So the mantissa, as I told you before, is you look at the normalized number and whatever is after the decimal here is the mantissa. So if it's 0, that means we fill up all the mantissa 23 bits with zeros. So now if I write down the sign bit is one bit here, so which is 0, that's for the sign. Then for the exponent we have here 1, 2, 3, 4, 5, 6, 7 bits, but we need 8 bits, so the first one we'll fill it up with 0, and then we have 1, 2, 3, 4 ones and 0, 1, 0. So those are the 8 bits for the exponent. And then we have to fill up like 23 bits for the mantissa with all zeros until the end. Okay, so that's B. And now for part C, let's look at it again. So we have here 492.78125. Let's work on that. So we have for part C 492.78125, and the first part is to know the sign bit. It's a positive number, so it will be 0, and then we take the integer part and we convert it to the binary number separately, and then we take the fractional part and we convert it to binary number separately. So if you convert the 492 to binary number, you get 1111 0 1100, and then converting 0.78125 to binary gives us 11001. And then what we do is we normalize the values. So we have now the value is 4 ones, 0 1 1 0 0, decimal, then we have 1 1 0 0 1. So to normalize this here, we have to move the decimal point to this position here. So we have to move 1 2 3 4 5 6 7 8. So we shift 8 positions and we'll have the number as 1.001. 1 1 1 0 1 1 0 0 1 1 0 0 1 times 2 to the power 8. Since we move towards the left here, so it will be a positive 8 now. So that's the normalized number here. So that's the normalized number. And again, when you get the normalized number after the decimal, all this is your mantissa. All this number is your mantissa. All right. Now, once we have normalized the value, what we do now next is add bias. So yeah, I don't want to repeat writing all those numbers again, so I'll just write for the bias. Now we have 8 plus 127, which is 135. And then if you're converting the exponent 135 from base 10 to binary, you get the number 1 0 0 0 0 1 1 1 in base 2. So that's the binary number. So we are done with all the conversions now, and what we now need to do is put it all together. So for the sign bit, we have here 0, and then for the exponent, we have here, so we have here 4 digits, that's 8. So we'll just write as it is now, 1 0 0 0 0 and 111. That's the exponent bit. So this is for the sign bit, 8 digits for the exponent, and then we'll fill up the 23 bits now for the mantissa. So we start from the triple ones here. So we have 111, 011, and then we have 0011, 0011, 001. So that's how many digits here now? It's 13 digits. So we are left to fill up 10 more. So those will be all zeros here. That's 23 bits for the mantissa. And that's the end of task 3.